Okay, you're welcome to today's presentation for the course ENGI 9858 Advanced Power Systems. And the topic of this presentation is reactive power compensation. And it's submitted by Jefta Oimai, Agui Chukwuemeka, and the instructor of this course is Dr. Ashraf Ali Khan. So, during the course of this presentation, we're taking you through the introduction, the definitions, why do we need reactive power, need for reactive power compensation, method of compensation, static VAR compensators using MATLAB, conclusion and references. So the demand of reactive power is mainly originated from inductive load connected to the system. So this inductive load are generally electromagnetic circuits of electric motors, electrical transformers, distribution network, and induction furnace. By using new emerging technology, the stability and reliability of the system can be maintained. And these devices that we use are called the flexible alternating current transmission systems. It is meant to enhance controllability and increase power transfer capability of the network. So you can see from this diagram reactive power, apparent power, and real power. So the real power, which is the active power, is the power that the equipment actually needs to perform its useful work. The reactive power is the power that the magnetic equipment, which can be the transformer or the motor, needs to produce magnetizing flux. And the apparent power is just the summation or the vectorial summation of the active power and the reactive power. So why do we need reactive power? In resistive load, the current produces the heat energy which produces the desired output. But in the case of inductive load, the current creates the magnetic field which further produces the desired work. Therefore, reactive power is the non-working power caused by the magnetic current to operate and sustain magnetism in the device. Reactive power is required to maintain the voltage to deliver active power through transmission lines. When there is not enough reactive power, the voltage sags down and it is not possible to deliver the required power to the load through the line. Reactive power compensation is defined as the management of reactive power to improve the performance of AC systems. So the need for reactive power compensation is for one, load compensation and also voltage support. For load compensation, the main objectives is to one, increase the power factor of the system, to balance the real power drawn from the system, to compensate voltage regulation, and of course to eliminate current harmonics. Then for voltage support, the main purpose is to decrease the voltage fluctuation at every given interval of the transmission line. Therefore, you can see the reactive power compensation improves the stability of the AC system totally by increasing the maximum active power that can be transmitted.
Reactive power compensation can be done through different means. One of such methods is shunt compensation. Shunt compensation requires the use of a shunt compensator, which is a device that is installed in parallel with the transmission line. A shunt compensator is always connected in the middle of the transmission line. It can be provided by either a current source, a voltage source, or a capacitor. An ideal shunt compensator provides the reactive power to the system. Shunt-connected reactors are used to reduce the line over voltages by consuming the reactive power, while shunt-connected capacitors are used to maintain the voltage levels by compensating the reactive power through the transmission line. Another method for reactive power compensation is the series compensation. In series compensation, we make use of a series compensator, and this device is connected in series with the transmission line. Unlike the shunt compensation method, the series compensator can be connected anywhere in the transmission line, and it has two modes of operation: the capacitive mode of operation and the inductive mode of operation. The final method of reactive power compensation we will be looking at is the use of synchronous condensers. Now, this is a device whose main function is the improvement of power factor of the electrical system, and it is installed at the receiving end of the line. When a synchronous condenser is introduced, it supplies reactive power to the system, and hence the current is reduced. When this happens, the losses are reduced and provides for better efficiency, and more power can be delivered to the load, which improves the power factor of the system. For this presentation, we will be simulating the use of a static VAR compensator to show how reactive power can be compensated. Now, a static VAR compensator is an electrical device for providing reactive power on transmission networks. The term static refers to the fact that the static VAR compensator has no moving parts, well, other than the circuit breakers that disconnect but do not move under normal operation. This device is an automated impedance matching device designed to bring the system closer to unity power factor, as we would see in this simulation. If the power system's reactive load is capacitive, the compensator will use reactors, usually in the form of tensor-controlled reactors, to consume VARs from the system, lowering the system voltage. Under inductive conditions, the capacitor banks are automatically switched in, thus providing a higher system voltage. Now in figure 1, we can see this model consists of a 6000 mega VA resistance and inductance power supply branch, a 200 megawatt load, a transformer with a transformation ratio of 735 to 16 kV, and a capacity of 333 MVA. Now running this system, figure 2 and 3 shows the graph of the reactive power and the power factor. In figure 2, we can see the graph of the voltage and current, which have a significant phase difference, and also in figure 3 we can see that the power factor is about 0.3, which is really poor for our system and begs for compensation. In figure 4, we can see that the static VAR compensator has been added to the system. This static VAR compensator will be emitting 256 megaVAR to the system in order to restore the voltage to the reference voltage. Now, the most telling part of the simulation can be seen in figure 5 and 6, where in figure 4 we can see that the voltage and the current are now almost completely in phase, and the reactive power which is being supplied by the source has significantly reduced, with the rest being supplied by the static VAR compensator. In figure 6, we can see that our power factor has increased to almost unity, which is a sign of a very efficient system. The static VAR compensator can maintain the voltage of the power system within plus or minus 10% of the reference voltage, which significantly improves the power system voltage stability. At the same time, it also plays a role in increasing the power factor, reducing losses, increasing the grid's transmission capacity, and improving the quality of user voltage. From the slides and the simulation carried out in this presentation, we can come to a conclusion that reactive power compensation is necessary in order to improve the performance of an AC system. And through reactive power compensation, we can control the power factor and reduce the consumption of electricity. These are the references employed in this presentation. Thank you for listening.